We merge special relativity and quantum mechanics into quantum field theory. We use the path integral approach to quantize our theory. We generalize the many-path formulation of quantum mechanics, where we replace the dynamical variable, which was the position of a particle, by the amplitude of the field at each point of space. We got a path integral, which is written for a sum of paths going from vacuum to vacuum over an infinite time. We found the classical limit by requiring the action to be stationary, giving the Euler-Lagrange equation. We also mentioned that there is another way to quantize our theory. So in quantum mechanics, we can get there by canonical quantization. The starting point of quantum mechanics in this case is to require the dynamical variable and its conjugate momentum to not commute. This is, for instance, the case for the position and the linear momentum. We know that their commutator is equal to I in quantum mechanics. But this can be generalized to any dynamical variable for which the canonical momentum is obtained by taking the derivative of the Lagrangian with respect to the time derivative of the dynamical variable. This is something we could generalize for field. We know that the dynamical variable now is the amplitude of the field at each point of space, and the canonical momentum density can be obtained by taking the derivative of the Lagrangian density with respect to the time derivative of the field. For many dynamical problems, we are interested in the time evolution, so we want to predict the future, and for that we invoke Noether theorem, which tells us that if we have an invariance of the action under time translation, then we have a conserved quantity, which is the energy, or in other words, the Hamiltonian. So we can get like that a Hamiltonian density for fields, which is expressed as the canonical momentum density times the time derivative of the field minus the Lagrangian density. And this is all we need in order to generate a translation in time for our system and therefore predict its future evolution. We also saw that particles emerge from quantum field theory as disturbance of the field which propagates on mass shell. However, we left a question unanswered in that we don't know how many particles we excite when we disturb the field. It makes sense to imagine that the larger the amplitude of the excitation, the larger the number of particles. However, we don't even have to have this number of particles as an integer, because we could imagine that we excite the field with some amplitude which will correspond, for instance, to 1.5 particle excitation. So there is something unsatisfactory here, in particular when we want to describe a process like the one we're interested in since the beginning, the collision of an electron with a positron through the exchange of a photon and a Z-naught producing a muon and an anti-muon. We see that here we are interested in only one incoming electron and one incoming positron. It turns out that this question, how many particles do we excite, is better answered in the case of canonical quantization. So we will now turn to this approach to quantum field theory, and in particular we will build our Hamiltonian using canonical quantization, because that will tell us how much energy is associated to a particle, and we will find that the spectrum of energy is quantized, and therefore what we call a particle is a disturbance of the field which propagates on mass shell, but which corresponds to a quantum of energy.